In today's video, we want to solve a question about function derivative. Here is the problem definition. We are given a function yx, which is equal to x multiplied by e to the power of 3x. It has 5 parts. In part A, we are asked to find its derivative. How to do that? We use the product rule. What is product rule? So product rule is like this. When we have a function that is the multiplication of two internal functions, we can use this equation to calculate the derivative of the overall function. Let's put ux as x and vx as e to the power of 3x. So now we need to calculate the individual function derivatives. So we use the chain rule, and for dv over dx, we can, using chain rule, we can obtain that, which is 3 e to the power of 3x, and du over dx is y, because u is x. So just substitute these two into the overall dy over dx. We can get that dy over dx is 3 multiplied by x multiplied by e to the power of 3x plus e to the power of 3x. In part B, we are asked that we need to prove by induction that the nth derivative of yx is equal to this equation. So in using induction, we try to obtain the result for n equal 1. Then we assume n equal k is correct and try to obtain the result for n equal k plus 1 by using the result from n equal to k. Let's do it for this problem. So we already have the result for n equal 1. N equal 1 is first derivative, so we have it from part 1, part A. So dy over dx is 3 multiplied by x to the power of 3x plus e to the power of x multiplied by 3 to the power of 0, which is 1. So now we assume that the expression is correct for n equal k. Means kth derivative of yx over x is 3 to the power of k multiplied by x multiplied by e to the power of 3x plus k multiplied by 3 to the power of k minus 1 multiplied by e to the power of 3x. Now we want to obtain the k plus 1 derivative. So k plus 1 derivative of y is derivative of kth derivative of y. Means we need to take a derivative from the expression for kth derivative. So this one is this one. So d over dx of 3 to the power of k multiplied by x multiplied by e to the power of 3x is 3 to the power of k, which is a constant, come out, multiplied by d over dx of x e to the power of 3x plus, again, the constant can come out of the derivative function, k plus k multiplied by 3 to the power of k minus 1 multiplied by d over dx of e to the power of 3x. So how to calculate this? So we can use the result from the first part, which is d over dx of, or if you look at this, our original function is this one. So we already have the result for d over dx of x multiplied by e to the power of 3x from part A. So we substitute part A here, and here d over dx of e to the power of 3x is 3 multiplied by e to the power of 3x. So we can obtain this equation for n equal k plus 1. So we can say that this is true for each n. So in part C, we need to find the coordinate of any local extremum point, means maximum or minimum, on the graph of yx. and we want to justify if it is minimum or a maximum point. So a general strategy to find the local minimum or maximum points on a graph of y(x) is finding a function derivative and set it to the 0. So first derivative, we set the first derivative to 0. So we use the result from part A, which is the first derivative, and we equal this one to the 0. So if we factor out e to the power of 3x, and the result is like this. So e to the power of 3x cannot be 0, right? It's not possible. So from part B, we can get some x. So we can equal 3x plus 1 equal to 0, and we can obtain that x is minus 1 over 3. And then we can find the coordinate of this point, yx, and by substituting x as a minus 1 over 3. And then the result is minus 1 over 3e. So we find the local extremum of yx is this point. Now we want to justify if it is a minimum or maximum. How to check it? So the trick is using the second derivative. We check the sign of second derivative. So we calculate the second derivative of function at the extremum point and see if it is positive or negative. So the general strategy is like this. The concavity is upward, means is a local minimum when the second derivative of y at that extremum point is positive. And when it is negative, we can say that the concavity is downward, so we have a local maximum. So you use the general equation. We can use the general equation, or we can also take a second derivative from the first derivative. We use the general equation. We set n equal to, and this is the second derivative of y. Now we substitute x equals minus 1 over 3, and then we obtain the value of the second derivative, 3 over e, which is positive. So it means that this point is minimum. So in the fourth part D, we need to find the coordinates of any points of inflection on the graph of yx. Justify whether any such point is a point of inflection. So inflection point is where the concavity of the function is changing either from downward or upward. From upward to downward means changing. No difference in the direction. So we need to determine it in two steps. Step 1, we set the second derivative at 0. And in step 2, we check the changes in the sign of second derivative around that point. So in step 1, we have the second derivative from here is this one. Is this one. So we set this one to the 0. So if we factor out this e to the power of 3x, we can get e to the power of 3x multiplied by 9x plus 6. So we set this one to the 0. So e to the power of 3x cannot be 0. It's not possible. We know that. So part B means the linear part can be 0. And then the x is minus 2 over 3. We can find a y coordinate by substituting x coordinate into the y equal to x to the power of 3x. And then we find the y. Now we need to check the sign around this point. So second derivative is 0 in this point. Okay, now we need to check the sign of the second derivative. How to do this? So we make a sign table like this. Second derivative, it is multiplication of two expressions, e to the power of 3x and 9x plus 6. E to the power of 3x is always positive. We know that. It's always positive. So the sign of the second derivative is determined by the sign of this linear part, because this linear part, it can be positive, and it's because it's a positive linear relationship between x and this linear part, so it can be also negative. So we use this sign table. So the point that we found the second derivative is 0 is in the middle, and we come from minus infinity to the positive infinity. Minus infinity, if we put minus infinity in the function of second derivative, we found this is negative because the x is negative. When x is smaller than minus 2 over 3, this linear part is negative. And then when we put the positive x larger than minus 2 over 3, the x, the linear part will be positive. So our second derivative function is changing from negative to positive. Means the concavity change. So this point is really an inflection point. So one note here is that in the inflection point, first derivative of y should exist. So if a function undergoes concavity change around the point, but no first derivative exists, that point is not an inflection point. Okay, in part E, and we need to sketch the graph of yx, indicating clearly the points found in part C and D, and any intercept with the axis. So till now, we have 2 points coordinates from the graph. We have a local minimum and an inflection point. Let's put it there on the graph. To sketch it, we can calculate the function in minus infinity and plus infinity. And also we can put the 0 and 0 there. Our function, our curve passes through the 0, 0 point. So it's in minus infinity, y goes to the 0. And in positive infinity, it's in positive infinity, y is going to the infinity. So we can, and also as I said, and our curve passes through the point of 0 and 0. So now we can draw our graph like this. That's the end of today's question. Thank you for watching.